All right, welcome. We're diving into the art and science of picking the right predictive model. I mean, you've got this mountain of data. How do you turn that into the best possible crystal ball? So let's just jump right in with a big question. Why isn't the simplest model always the best one? We hear keep it simple all the time, right? But in the world of prediction, a super simple model can get totally tripped up by messy real-world data. So the real question is, when do we need to bring out the big guns?
Okay, so it really boils down to this classic trade-off. On one side, you've got pure prediction accuracy. You just want a model that nails it, that predicts the future correctly. But on the other side, you have model interpretability. You actually want to understand why the model is making the calls it's making. And here's the problem. The most accurate models, they're often these crazy complex black boxes. The simplest ones, super easy to explain, but maybe not as sharp. This is the dilemma, the balancing act that every single data scientist faces. And this dilemma, this core conflict, has led to basically three different schools of thought, three different philosophies for building better models. Yeah, you can think of these as three different characters you can call on. First up, you've got the minimalist. They're all about choosing only the most essential predictors. Then there's the disciplinarian. They keep all the predictors, but they really rein in their influence. And finally, you have the alchemist, who just transforms the whole mess of predictors into a few powerful new ones. All right, let's get into path number one, the minimalist. This whole approach is about one thing, picking only the absolute best players for your team and leaving the rest on the bench. So a really common way to do this is something called forward stepwise selection. And the idea is actually pretty clever and efficient. See, trying to test out every possible combination of predictors, that would literally take forever. So instead, you do it step by step. You start with nothing, a totally empty model. Then you add the one single predictor that gives you the biggest bang for your buck. It's kind of like a sports draft. At each round, you just pick the most valuable player available. The process itself is super systematic. You start with a null model, right? No predictors at all. Then you look at all your available predictors and ask, which one of you, all by itself, gives me the best possible model? You pick that one, lock it in. Then you do it again. You say, okay, now that I have that one, which new predictor gives me the biggest improvement? And you just keep repeating that process until adding new players to the team just doesn't make it any better. But, and this is a big but, there's a catch. This step-by-step method has a blind spot. It's what we call a greedy algorithm, meaning it only makes the best choice for the current step without thinking about the future. And you can see that right here in this example. For models with 1, 2, or 3 variables, forward stepwise actually finds the same best combination as a more exhaustive method. But look at the 4-variable model. It misses the absolute best combination. Why? Because a choice it made early on kind of blocked it from finding a better path later. So yeah, it's fast, but it's not guaranteed to be perfect.
Okay, on to our second philosophy, the disciplinarian. The idea here is totally different. It's not about firing players. It's about keeping everyone on the team, but managing them, putting some rules in place to control their influence. And the first tool for this is called ridge regression. What ridge does is it keeps every single predictor in the model, but it puts a penalty on them. It basically shrinks their coefficients, their level of influence, pulling them closer and closer to zero. This is so important for stopping a model from overfitting. That's when it starts memorizing noise instead of learning the real signal. It's kind of like a salary cap in sports. It just stops any one predictor from becoming too powerful and throwing the whole model out of whack. And then you've got the lasso. And if ridge is a disciplinarian, the lasso is it's a much stricter one. It also shrinks coefficients, but the way its penalty works is different. It's so tough, it can actually force some coefficients to go all the way to exactly 0. And this is a huge deal, because it's not just reducing a variable's influence, it's literally kicking it out of the model. The lasso does automatic variable selection for you, which can give you a much simpler, easier to understand model. So if you want the key difference, here it is. Ridge regression is like a gentle moderator. It keeps all the variables in the model, but just kind of quiets them down a bit. The lasso is more like a ruthless coach. It will literally bench the weakest players, setting their influence to 0 and creating what we call a sparse model with only the most important variables left standing. Okay, that brings us to our third and final path, the alchemist. This approach is maybe the wildest of them all. It doesn't just pick from your original predictors or shrink them. No, it literally transforms them into something totally new.
And the most famous of these alchemist methods is called principal components regression, or PCR. This is an amazing tool for when you have a ton of predictors that are all kind of tangled up and correlated with each other. What PCR does is it takes that whole messy web and distills it down into a handful of brand new, uncorrelated variables. We call these principal components, and each component is basically a recipe, a new feature made from a blend of the original ones, and it's designed to capture a big chunk of the information in your data. So it's really a two-step process. Step 1 is where the magic happens. It finds these new features, these principal components that explain most of the variation in your original predictors. Then, step 2 is super simple. You just run a regular linear model, but instead of using your old predictors, you use these new, powerful components. It's a really smart way of simplifying the problem before you even start predicting. But this brings us to PCR's big weakness, its potential Achilles heel. Remember how that first step is unsupervised? It only looks at the predictors, not the thing you're trying to predict. Well, because of that, there's absolutely no guarantee that the directions that best explain your predictors are also going to be the best directions for predicting your outcome. You might create this beautiful, elegant summary of your input data that turns out to be totally useless for the actual task at hand. So, okay, we've got these 3 totally different philosophies, right? The minimalist, the disciplinarian, the alchemist. We have all these competing methods. So, for your specific problem, how in the world do you pick a winner? And this, right here, might be the single most important question in all of predictive modeling. See, we don't really care how well a model did on the data we use to build it. That's like giving a student the answers to a test and then being impressed they got an A. It's just memorization. What we really care about is how well it performs on new data it has never seen before. We need a way to estimate its test error. And broadly speaking, there are 2 ways to get at this. First, you have indirect methods. These are things like AIC or adjusted R-squared. They basically look at your performance on the training data and then apply a statistical penalty for how complex your model is. The more complex, the bigger the penalty. Then you have direct methods, which are way more, well, direct. They don't just estimate, they try to actually measure the test error by setting aside some data that the model never gets to see during training. And really, the gold standard here is a technique called cross-validation. It's such a brilliant idea. You basically take your data and split it up, let's say into 10 chunks. You train your model on 9 of those chunks, and then you test it on the 10th one that you held out. Then you do it again, but you hold out a different chunk. You repeat this whole process 10 times so that every single chunk gets to be the test set once. When you average out the performance across all those runs, you get a really solid, trustworthy estimate of how your model will actually do in the real world. And that's really the key takeaway here. There is no single best method that wins every time. It's all about trade-offs. You know, the lasso can be a lifesaver when you think only a few predictors really matter. Ridge might be your go-to when you think lots of predictors have small but important effects. And PCR can be a game changer when your data is a tangled mess of correlations. A really skilled modeler doesn't have one favorite hammer. They know how to use every tool in the toolbox. And this kind of leaves us with one final big question to think about. As all these tools get smarter, as techniques like cross-validation become more and more automated, is building the perfect model becoming less of an art and more of just raw automation? Where do we draw the line between human intuition and pure algorithmic power? That's a question we're all going to have to grapple with as we move forward.